Do you need the functionality of a benchtop PNA but in a smaller form factor that's easier to move between labs? Learn all about the new Keysight Streamline Series VNAs and how they can help accelerate your design process. These new VNAs are USB compact instruments which are great for transporting between labs and test floors. They are all 2-port models and range from 4.5 to 26.5 gigahertz. In this video, you will learn about how to get the new VNA set up and calibrated, and how to do some basic testing with it to ensure you're making accurate measurements. The materials we'll be using in this video, aside from the instrument itself, are an eCal module, a male-to-male SMA cable, a bandpass filter as our DUT, and a 3.5mm torque wrench. So, first things first. Before we actually dive into how to use this new type of instrument, we have to get the software downloaded and ready to use on our PC so that we can actually control this box. The first thing you have to do is download the Keysight I/O libraries at the link on the screen. This is what will allow you to connect instruments to your PC and manage those connections. You need this for almost all of Keysight's software, so you may already have it installed on your computer if you use software like BenchView, but be sure to check that you have the latest version in order for it to work with these new USB VNAs. The firmware is what will actually allow you to control the instrument on your PC. You can find this link in the description below as well, or you can find it under the support section of the web page. Once the firmware is installed, it will prompt you to restart your computer. After the restart, you'll see an icon for the software on your desktop. Before you open the software, plug in the USB cable of the instrument into your PC. Once you do this, open the new VNA software by double-clicking the desktop icon. Your device will show up in that window. Select it and click Run. Notice that this soft front panel has the same user interface as the Keysight Benchtop PNA and ENA, as well as the modular PXI VNA. This makes it really easy to move between different form factors in your various design phases. To get set up, I'm going to connect the SMA cable to test port 2 and the DUT. I'll also connect the eCal module to the host PC using a USB cable. Next, we need to set up and calibrate the instrument, which is actually easier than it sounds. The calibration and quick setup tools can help you quickly get your test parameters set up and ready to go. The quick setup function guides you through the entire setup process with a variety of templates for fundamental measurements. Always start out with the preset button to reset any settings the previous user may have left. We'll go into the setup menu and select Quick Start to show the setup dialog. Since we are only working with one port here, I'll select the one port S parameter option. This is where you will need to enter your start and stop frequencies, sweep type, power level, and the other parameters for your test. It's important to remember here that this new USB VNA's source power must be set correctly in order to avoid damage or compression inside the eCal module. The power for this should be set to -15 dBm for the calibration operation. Now that we're done with that quick setup, let's get calibrating. The eCal module is used for this calibration to remove system errors, like the effective test cables. Wait until the LED of the eCal module turns green, indicating that it has warmed up enough in order to correctly calibrate. Once the module is connected, start the calibration by going to the Cal menu, selecting Other Cals and eCal. We're going to do 2-port eCal and leave the default settings. Select Measure. Once the calibration is complete, you will see a message like this pop up on screen showing that the calibration has been saved to the channel. Now, let's connect the DUT to port 1 and the test cable coming from port 2 and ensure we can see the signal on screen. We can see the measured S11 parameter in magnitude on the screen as the default parameter, just as we set in the quick setup. Let's take a look at the S21 parameter, which is the transmission between port 1 and 2. We'll do basic data analysis of our DUT, which is a bandpass filter. Add a new trace by clicking the Add Trace icon from the top toolbar. The S11 trace will probably pop up on the screen as a blue trace. We're going to change the parameter of this trace to S21 instead. Select Measure and S21. Move Trace 2 on the screen in order to show the two traces side by side by dragging Trace 2 on top, and now you can see S21 on the right side of the window with S11 on the left. So you can really easily set up the layout of how you want to view each trace. Let's rescale this S21 signal to see more detail by dragging the reference marker on the Y-axis up to show the entire response on screen. Using a marker on this trace, I can measure the maximum power of the trace. Using the marker and max search functions, I find the max value is about minus 1.6 dB, which means we have about minus 1.6 dB insertion loss. We can also easily analyze the bandwidth of this bandpass filter we're testing by pressing Select and Bandwidth and Notch. Just press Bandwidth Search to analyze the bandwidth. You can also view these traces in different formats. Let's say I'd like to see the Smith chart for this S11 trace so that I can characterize the matching of this bandpass filter we're testing. So I'll select Format and Smith. You can see all the different formats available, the standard log mag, a phase chart, polar, delay, and so on. These different views help to characterize the different aspects of your device. Lastly, let's learn about how to speed up measurements and improve their accuracy. First, I'll double-click on the S21 window to maximize that on screen. In order to speed up the measurements, we need to make the intermediate frequency bandwidth, or IF bandwidth, wider. The wider the IF bandwidth is set, the faster the measurements can be performed. So let's set the IF bandwidth to 300 kHz by going to Average Bandwidth, IF Bandwidth, and enter that frequency. However, the trade-off is the higher the IF bandwidth is set, the more random noise will be introduced to the measurement. You can see that increased noise here in the rejection bands below 350 MHz or above 2 GHz. To improve this signal-to-noise ratio to make more accurate measurements, we can increase the instrument's source power. I'll select Power and Power Level and enter 7 dBm. You can instantly see that the trace noise in the rejection bands has improved while maintaining that high measurement speed with 300 kHz IF bandwidth. These are just a few helpful tricks to help get you up to speed with the new Keysight Streamline Series USB VNA instruments. Now you'll be ready to go with the quick setup and easy calibration process. And now you understand how to make more accurate measurements with the instrument right off the bat. To learn more information about the Keysight Streamline Series, head over to the links you see here or in the description.